There we go. So the homework assignment that is due today covers sections 9.2 and 9.3. You should have gotten a Dropbox invite for that last night. And I've noticed a few people have already submitted that assignment, which is great. I may not have time today in my class to actually take questions on the homework. I'm not sure yet. Since it's a pretty short assignment, I may defer those questions to my Zoom office hours later on after class. So people can certainly come by and ask me questions about it, but I may or may not get around to questions during our formal session today. I have quite a bit of stuff I want to try to cover today. So that's the homework that's due today. Now, for Thursday, there will be no homework due. However, I'm going to recommend that you start working on this next homework assignment before Thursday so that you can ask me questions on Thursday about it. The next assignment after the one you're turning in today is a little bit longer, and it's really important for the material that you're going to need to know. So it would be a great idea to start the next homework assignment as soon as you can. So that you can give it some good attention. It's not due on Thursday because some of the material for that assignment I will be talking about on Thursday. So what I have done, and you'll notice this on my website homework screen, is the next homework is going to be due on Saturday. I know that's kind of a strange time to have a homework assignment due, but that way you'll have enough time to learn the material both today and Thursday so that you can turn in that assignment by Saturday. I'll try to add some extra office hours maybe on Saturday as well, in case people do want to talk to me on Saturday about things. But the reason for this somewhat accelerated schedule is because we have a midterm next Tuesday. So 1 week from right now is our third midterm. And we're going to run it more or less the same way that we ran the second midterm. You might remember right before spring break, we had to do a virtual midterm, and where I basically email you the midterm, you work on it, and then submit it to a Dropbox folder a couple hours later. That's basically what we're going to do with the third midterm as well. So I've got a tab on my website that has a bunch of stuff that will be helpful to you while you're studying for the third midterm, right? It has a review packet. It has some practice problems with solutions worked out for them. I've got a sample midterm up there for you, solutions to that sample midterm. I've got some review session problems. Now, I'm not going to be doing a physical review session again this semester, obviously, with this whole virtual learning thing going on. However, last semester, I recorded a beautiful 3-hour video of a review session that covers exactly the same problems and exactly the same material. So I have posted that review session in its entirety. You can watch that video, and I would recommend that you do that and you follow along and work out the problems with me in that 3-hour review session. You could take a look at that over the weekend, for example. Also, by now, we probably, if we had been in McCarthy Hall, we would have taken a quiz. We're not doing that in light of the virtual learning that's going on. But I did post a sample quiz and the solutions to that as well. It's all available to you on my website. So what I'm saying is that now that we're about a week out from our midterm, this would be a good time to start reviewing for the test. It's going to go all the way back to where we left off at spring break. So the kernel and range of a linear transformation, right? This is in chapter 6. One-to-one and onto linear transformations. And then all of the stuff on eigenvalues and eigenvectors and their applications and the theory, all of that will be something to look over again. And then all of this more recent material where we've gone back to differential equations again. You know, we looked at nth order linear differential equations in chapter 8. And now in chapter 9, we're looking at systems of differential equations. And so it's a pretty big coverage of material for this midterm, but your final exam is only about 9 days after that midterm. And if you study well for this midterm right now, I guarantee that not only are you helping yourself out on the midterm, you're also pre-studying for the final, because the material in this course is so cumulative. It's so comprehensive. It continues to build on what we learned before, that if you're on top of things for the third midterm, you'll have a lot less to stress about the following week when it's time to get ready for the final. So this would be a great time. I know it's a crazy time, but it would be a great time to try to kick things into high gear, really try to get on top of this stuff. As far as chapter 9 goes, last Thursday I started chapter 9 and I covered sections 9.2 and 9.3. Don't worry about section 9.1, by the way. That's not really something that we've spent any time on. But I covered 9.2 and 9.3. We're now going to cover sections 9.4 and 9.5 this week. Both of these two sections are a little bit longer and they involve a little bit more background. So we're going to have to spend some time on these sections. If possible, I'll try to get it all covered today and Thursday. I might supplement with a video or two as well, just to give you some extra practice with the stuff. But anyway, that's kind of what we're going to be working on this week is 9.4 and 9.5, and that's what the homework for Saturday. Again, your next homework assignment is due on Saturday. That's what it'll be based on. Okay, are there any questions about the logistics, how this next week is going to lay out? Okay, if that's all very clear, I want to get back right into the math today and try to cover section 9.4. As I said, it's a little bit longer section, so we'll need some time to get through it, but it's really cool stuff. I think you're going to like it. Okay, so we're talking about linear systems of differential equations here. This is all just the recap from last week. In this box, you see the main equation for chapter 9. X prime, which is a vector x, the derivative of the vector x, equals an n by n matrix A times x. So this is all represented as a matrix system. I'm going to label it with a star for right now. The goal of this whole chapter is to solve for x. X is your unknown column vector. And within that column vector, you have a bunch of individual unknown scalar functions. x1 of t, x2 of t, x3 of t, right? That's what's filling up that column that makes up the x vector. So the goal is to solve this boxed equation for x. Now, one of the first things that we mentioned about looking for those solutions to that boxed equation is that those solutions form an n-dimensional vector space. Okay, so the linear algebra is here front and center again. We have a vector space, and the dimension is n, which means that all we really have to do to find all of the solutions to our box here is find n linearly independent solutions. And these will be vector solutions, right? Every single thing that's a solution to this system is a vector at this point. This is what chapter 9 is about. Okay, so it turns out we have a test here for linear independence in chapter 9. And it's a Wronskian test, but it's a different Wronskian than the one that we learned in chapter 8. What it says is that if we take the determinant of all of our n vector functions that are laid out into the columns of a matrix. So this is going to be a square matrix whose columns are those vector functions that we are testing for linear independence. And if that determinant is not 0, or in other words, is not always 0. So if it's not 0 for at least one value of time, let me call that value t naught, then you can conclude that your functions form a linearly independent set. And that's great, because if they are linearly independent, then they're going to form a basis for this n-dimensional vector space that we're looking for. Okay? And that's how we find all of the solutions to our system. We need n linearly independent solutions that we can test with the Wronskian for linear independence. And then we've got our basis for the solution set. I didn't mention this last Thursday, but here at the bottom, I put a definition down that is just kind of helpful to know. When you have n linearly independent solutions to your vector space, to n linearly independent solutions to your linear system of differential equations, those solutions are called a fundamental set of solutions. Okay, so this is a lingo that differential equation specialists will use. A fundamental set. It's really just another word for a basis, right? It's a basis of solutions. And if we actually think about the matrix that we can build, this matrix whose columns are those solutions, that is sometimes called a fundamental matrix. Okay, so we have a fundamental set of solutions and a fundamental matrix. Okay, so this is a lot of material on the board here. It's a lot of that's just recap from last week. I'm going to erase it in a minute, but don't worry. I'm recording this session, and you'll be able to go back if you need to and watch it again, or copy snippets of my whiteboard in case you might have missed anything. Okay. Now, one thing that you have not missed so far that you're probably wondering about is you're thinking, well, that's great, Dr. Annan. Once I have n linearly independent solutions, I'm in good shape. But how do I get those solutions, right? How do we actually solve this system of differential equations? That we did not talk about last week, and that's what we're going to get into right now. Okay, so I'm going to go ahead and erase most of this board. And we're going to start talking about that problem. Okay, so that's the question that's on everybody's mind, right? Is how do we get n linearly independent solutions? The answer to this is a beautiful thing. It's very linear algebra oriented, and it's the following. When I say it's a beautiful thing, I mean, what I mean by that is it relates so nicely to something that we learned recently, which is that the answer lies in finding the eigenvalues and eigenvectors of the matrix A. It's a square matrix. It's going to have n eigenvalues, and therefore, you know, you can find corresponding eigenvectors and so on, right? So here is the answer, right? Suppose that lambda and v is an eigenpair of the matrix A. Suppose you actually have an eigenpair right there. Okay, then what I'm going to do is I'm going to consider, here is the magic solution that we're going to now construct. I'm going to make x of t to be the following thing: e to the lambda t times v. This is so beautiful that the eigenpair, the eigenvalue eigenvector pair, shows up right here. By the way, let me just remind you, the eigenvalue eigenvector relationship, the most important equation in chapter 7, right? And so I'm sorry, Omar, you're asking me to scroll down a little bit. Are you okay? I'm not quite sure what you mean by scrolling. Oh, you wanted me to just turn this down a little bit. I'm pretty much, I think I've got the whole board. Let me just back this up slightly. Hopefully everybody's able to see everything pretty well here. Okay. Let me just remind you about this eigenpair equation. It's going to be on the test next week. It's the most important equation for sure in chapter 7. And here it is. I'm sure you all remember it. AV equals lambda V, right? So that equation is really very important, okay? Especially for theoretical aspects of eigenvalues and eigenvectors. So we talked a lot about that in chapter 7, and it's coming back up here in chapter 9. Now, here's my proposal. Take your eigenpair, lambda and v, and build a vector function, which is e to the lambda t times v. Now, I have to verify that that actually works. Let's try it. Let's take the derivative of this. In other words, I'm going to plug this proposal into this box and see if it works. So I'm going to take the derivative of this function right here, and I'm differentiating, by the way, with respect to t. So these are derivatives with respect to t. Well, the derivative of e to the lambda tv, the derivative of e to the t is just lambda e to the lambda t. V is just a constant, so it kind of comes along for the ride. And what you'll notice is that you can actually put well, you can switch the order. So this is a scalar, and this is a vector. So you can switch the orders of some of these things, right? So I can, for example, put the lambda next to the v if I want. I can write the lambda next to the v. And my reason for doing that should be pretty clear, because I want to replace lambda v with av. So let me just do that right here. This is e to the lambda t av. And now I'm going to put the a back in front again. So I'm going to put the matrix in front, and then what I'm left with behind the matrix is e to the lambda t v. And sure enough, that is just a times x. X of t, if you want to include that, right? So x prime equals ax. It works beautifully. Here you go. You have a wonderful recipe for making solutions to these linear systems now. This is the first point that I wanted to get across today. Okay, is that all you have to do to make solutions to your linear system is find the eigenvalue, eigenvector pairs of your matrix. This makes sense? Now, of course, you know, there's some possible problems here. The first one is you're supposed to come up with n linearly independent solutions. That'll happen as long as you get n different eigenpairs. You can just build n solutions that way. But one of the problems is, what if the matrix is defective? Right? Remember from chapter 7, if a matrix is defective, it means that the eigenvalues do not all pull their weight. And you don't necessarily get the n linearly independent pairs or solutions that you are required to come up with, right? So when your matrix is defective, that makes things harder. And that's actually the topic of section 9.5, which I'm mostly going to be talking about on Thursday. So what I'm going to do right now is I'm going to ignore that problem. And in section 9.4, we're going to focus on non-defective situations. Okay? So let me go ahead and do that. So in section 9.4, the title of this section is non-defective coefficient matrix A. So suppose that the matrix is not defective, okay? So that's what we're going to talk about here. So in this case, okay, so in this non-defective case, we get n linearly independent eigenvectors, right? Remember, a non-defective matrix is just one that has n linearly independent eigenvectors. Let me give them names. Let me call them V1, V2, up to Vn. Okay, so you have n of these linearly independent eigenvectors. Let me correlate the corresponding eigenvalues down here. Lambda 1, lambda 2, all the way over to lambda n. Now those lambdas don't have to be distinct, by the way, right? The lambdas could repeat as long as the repeated lambdas pull their weight. That's okay, right? In that situation, as long as the eigenvalues all pull their weight, we have a non-defective matrix, okay? So this is my setup. I have a non-defective matrix, and these are my eigenpairs right here on the right-hand side, okay? So then we get, you know, x1 is going to be e to the lambda 1t v1, x2, all of these are functions of t. I won't keep writing that because it just takes too much space. x2 is e to the lambda 2t times v2, and so on, right? The last one is xn, which is e to the lambda n vn. Okay, so let me get out of your way here, make sure that you had a chance to read all of that. So I've just been building these solutions, x1, x2, x3, and so on. For my non-defective matrix, I have n solutions just like this. Okay, be sure to stop me. If you have any questions, feel free to type into the chat or unmute yourself. And you can certainly speak up. Don't be afraid to let me know if anything is confusing here. We're really into the sort of the heaviest part of the semester. This week, we've got a lot of stuff to get through, but we're almost there. That's the good thing. We don't have that much more to go. Once we get through this week, we'll have almost everything learned that we need to learn. Okay, great. Now, let's just use the Wronskian and check that these are linearly independent really quickly. We won't always do this Wronskian check, but in this case, let's just take a minute and do it. Let's do the Wronskian of x1, x2, up to xn of t. So this is the determinant of, remember the Wronskian, it's a determinant. How is the determinant created? Well, we just take our individual functions and put them into the columns of this matrix. So we do e to the lambda 1 t v1, and then the second column is e to the lambda 2 t v2. Column by column, we fill out the whole matrix just like that. The last column, e to the lambda nt vn. So this is my determinant that I'm going to calculate. Now, each one of my columns has been multiplied through by a scalar. So you probably remember way back to when we were actually face-to-face, seems like forever ago, but back in February when we were learning about determinants, right, we learned that when you multiply a row of a matrix through by a constant, the determinant gets multiplied by that same constant. The same thing happens if you multiply columns through by constants. Right? Here we have a matrix where each of these columns has been multiplied through by a scalar. I'm going to basically, therefore, use my determinant properties to pull those scalars out. E to the lambda 1t, e to the lambda 2t, all the way along the line, e to the lambda nt. Those are just numbers, right? These are just scalars that are multiplying the columns of this determinant that I'm looking at. And after I've pulled those out, what matrix is left to take the determinant of? Well, it's just V1, V2, all the way up to Vn. Okay? So I'm just calculating my Wronskian of all of these functions that are in this box right here. Now, the neat thing is, an exponential function is never going to be 0, right? E to the lambda t is never 0. So this is not 0. This is not 0. None of these scalars in front are going to be 0. They're all non-zero for sure. What about this matrix that we're left with over here? The columns of that matrix are my linearly independent eigenvectors. And I bet you remember that when you have a matrix whose columns are Li, so you have a square matrix and the columns are Li, one of the results in our big invertible matrix theorem, you know, parts A, B, C, D, E, F, G, H, I, J, K, L, M, N, O, P, in that big, huge, long theorem, one of the results says that for an invertible matrix, the columns will be Li. And another result in that same list says that for an invertible matrix, the determinant is not 0. So this is also not 0. The whole thing is not 0. Okay, so it's not 0. And that means that these functions are linearly independent. This is exactly what we wanted. Okay, so therefore the general solution, we have n linearly independent solutions. So the general solution to x prime equals ax. Right? How do we write down the general solution? Not just the way we always have, right? We're just going to write it down, you know, x of t equals, and now we're just going to start listing, you know, c1 x1 of t plus c2 x2 of t plus ... It's just a linear combination of these basis solutions, right? That's really what we're doing. So the last term, xn of t times cn. Okay? I can also explicitly write it out. This would be, you know, c1 e to the lambda 1 t v1. And then the second term is c2 e to the lambda 2t v2. And then plus ... Right? The last term, cn e to the lambda nt vn. And this is really the way that you normally are going to see it written. Okay? That's normally the way you're going to write it. Okay, I think it's time for an example. Okay? So let's do an example of this. Are there any questions? I should mention, guys, you're not going to have to check this Wronskian, right? We've just checked it right now once and for all that it's not 0. So every time we do an example, we're not going to come back and re-verify this Wronskian again. We're just going to go straight to the answer because we know that this calculation down here is always going to be the same and it's always going to work. So there's no need to like keep repeating it again and again. So we'll just jump to the punchline most of the time from now on. I just wanted to show it to you once at the beginning, just so you have a good belief that this really is giving me linearly independent terms up here. Okay, let's do an example. Let's do an example here. Let's find the general solution to x prime equals ax, where capital A is the matrix -2, -7, -1, 4. So we'll do a little 2 by 2 matrix here. Most of the time for the actual computational problems, the examples are going to be 2 by 2 or maybe 3 by 3. There'll be some 3 by 3s as well, but generally not larger than that unless the matrix is really, really nice for some reason. Okay, so this is just a 2 by 2 to get us warmed up with. Okay, so here's our problem. Solve x prime equals ax. I've got my matrix in front of me here. So the key to doing this, guys, is to find the eigenpairs, the eigenvalue, eigenvector pairs. So we're actually going to be doing a lot of review of what we learned in chapter 7, 2-3 weeks ago. It's going to come back up in this section as well. So I'm going to take the determinant. I'm starting with the eigenvalues, right? So to find the eigenvalues, I subtract lambda off of the main diagonal. Okay, and this is only a 2 by 2 problem, so I can handle it pretty easily with the formula for a 2 by 2 determinant, AD minus BC. So I'll go ahead and write this down. Make sure everybody's following along. This should be hopefully just old review here. So AD minus BC just gives me that. I'm just going to multiply this one out because it's only a quadratic after all. So I'll get lambda squared minus 2 lambda minus 15. And that actually factors nicely. So I'm going to do that. This is going to be lambda minus 5 times lambda plus 3. Lambda minus 5 times lambda plus 3. And that means that my lambdas are all distinct. I have lambda equals 5. And then I have lambda equals -3. These are my 2 lambdas. Okay, one of the unfortunate things is these problems take a bit of time and space in chapter 9, and I don't have a lot of space on my whiteboard. So you're going to have to be patient with me. I'm going to be doing some erasing to make room for my work and so on. It's just the nature of this particular chapter here at the end. Most of these problems take quite a bit of calculation. So we found our eigenvalues. Now we have to find the eigenvectors. So I'm going to do a null space here down in the lower left corner. I'm going to subtract 5 from the main diagonal of A, and that's going to give me the matrix -7, -7, -1, -1. Remember, back to chapter 7, that this matrix is never going to be invertible because you were setting the determinant. I forgot to do that over here. You're setting this determinant equal to 0, right? So when you set this determinant equal to 0, you're talking about a matrix that's not invertible. And this is definitely not invertible. You can see that the 2 rows are multiples of each other. Just go ahead and wipe off a row. Nothing wrong with doing that. And you can take this bottom row if you want, which is really just the same as 1 and 1. And we can pretty quickly spit out a vector from that. I'm going to use the vector -1 and 1. Okay? So this is my eigenvector that corresponds to the eigenvalue of 5. Okay? So I have my pivot right here. My free variable would be t. And then when I solve for the pivoted variable, I would get -t. Take that t and bust it out, and this is the vector that you're left with. Right. Okay, hopefully that makes some sense. let's do the other eigenvalue, and stop me if there's a question, but this is just chapter 7. Chapter 7 and chapter 9 actually tie together with each other very, very well. So it'll be good to kind of study them together as we're getting ready for our exam next week. Okay, so lambda equals -3. I'm going to do the null space of the matrix that I get by adding 3 to the main diagonal. So I'm going to get 1 and -7 and -1 and 7. And again, these two rows are multiples of each other. They have to be. So just cross one of them off. Just draw a line through it. Perfectly safe thing to do. You have your pivot right here, which is the 1 in the upper left. If you assign the y variable to equal t, then x is just going to be 7t. And when you bust out that t, you're going to get a vector here, which is going to be 7 and 1. Okay, so I have been doing the work of calculating my eigenpairs down here on the bottom. Let's go ahead then and write down the answer to this problem. We can write down the general solution at this point. Okay, so the general solution, pretty easy. X of t equals, okay, C1. So let's go to our first eigenpair down here. We have a lambda of 5 and the eigenvector -1, 1. So this just becomes e to the 5t times -1, 1 plus C2. The second eigenvalue was -3. So we get -3t and we get the vector 7 and 1. Okay, so there you go. That is the solution to that problem. Okay, any questions about that one? Most of the work actually is just finding the eigenvalues and eigenvectors, which we've learned how to do already towards the beginning of April. And then here we're just combining everything into a final answer. Okay, great. If everybody's comfortable with that, I'll leave it at that. I will make one note here. If somebody gave us an initial condition, so if we had an initial condition, I think there's one of these on the homework actually that you're going to be doing for Saturday. If we had an initial condition, this would be something like x of 0. So if somebody gave us a supplementary condition here, then we could solve for C1 and C2. The constants that are up here, this is in the general solution. If we had an initial condition, we would be able to solve for the constants and get a particular solution, right? So this would be to obtain a particular solution. A particular solution to what would then be, at that point, what you're talking about is an IVP, an initial value problem. So if somebody gives you extra conditions, these initial conditions, then that's going to allow you to solve for the constants. I don't think I'll do an example of that right now, but we'll look at examples of that a little bit later on. Okay, I'd like to do another example of this. Is everybody good so far? No questions yet? Okay. Now, we already mentioned earlier that if our matrix is defective, this might not work so nicely, right? We might not come up with, in this case, we would have needed 2 solutions up here to build our general solution, right? But if we didn't get a full set of linearly independent eigenvectors, we wouldn't be able to do that. So that's already one problem. But even if we stick with non-defective matrices, there's another problem that can come up. And I'm going to do another example that's going to highlight that problem. Okay? Let me erase, I think I'm going to erase the whole entire board here. So again, if you have not caught up on taking notes, this video is something you can come back to later. I want to do another example where we run into another problem. Even in a non-defective situation, there's another problem that we sometimes have to deal with. So here it is. Example. Okay. Find the general solution to x1 prime equals 9x1 plus 29x2 and x2 prime equals negative x1 minus x2. You might notice I did something a little different to you here on this example, which is I didn't give it to you in the matrix form to begin with. You don't have the matrix set up for yourself at this point yet, right? So I just wanted to practice one time, making sure that you guys can go from having these separate equations here to building it into a matrix, because I've done this on exams before where I didn't present it as a matrix to start with, and I've seen people build the matrix incorrectly, and you don't want to get that incorrect. So let me show you that essentially I can reformat this question by just doing this. I'm just going to put the x1 prime, x2 prime right here on the left side. I'm going to make my matrix right here in a minute, and then of course I'm going to have x1 and x2 like that, right? So we're just reformatting the problem so that it looks like a matrix now. Okay, so now we just have to put the numbers in, and you just have to make sure that you put the numbers into the correct places. Make sure that when you do your matrix multiplication, that it works out to giving you the equations that you see in the problem. So the 9x1 plus 29x2, is that what we get here on the top? 9x1 plus 29x2. Okay, that's x1 prime. And then x2 prime, that's negative x1 minus x2. So we're good in this whole setup so far. Okay, so now this, okay, I'm just going to come up here and recopy this. This is just x prime equals 9, 29, negative 1, x. I just want to put it up in the corner so I can have more room to write the rest of the problem. Okay? Any questions about that? I'm just reformatting the question into a matrix. This is my capital A right there. Okay, that's the capital A. Okay, so now let's try and solve this one. Again, we need to find the eigenvalues and eigenvectors. So I'm going to take the determinant of the matrix that I get when I subtract lambda off of the main diagonal. Okay, so we just take this determinant here. I'm going to go ahead and use my formula, 9 minus lambda, negative 1 minus lambda, and then plus 29. Okay, so that's using the AD minus BC determinant formula. Let's just multiply this out. It's only a 2 by 2 matrix, so that should be pretty reasonable. I get lambda squared minus 8 lambda, and then I have minus 9 and plus 29, so that's a net total of plus 20. This one does not factor so nicely when I set it equal to 0, but I can use the quadratic formula to find the lambdas now, and that's what I'm going to do So my lambdas are going to be 8 plus or minus the square root of 64 minus 80 all over 2. And I think some of you are probably already realizing what's going to be the challenge here. 8 divided by 2 is 4. But look at the square root here, guys. 64 minus 80 is negative 16. So we're going to get imaginary numbers because the square root of negative 16 is 4i. I divide that by 2 and I get 2i. 4 plus or minus 2i. These are imaginary values. Now, don't panic because in chapter 7, this happened to us before, right? We came up with matrices that had complex eigenvalues and complex eigenvectors, and it's not the end of the world. So let's just keep proceeding with this. Let me take my lambda equals 4 plus 2i, and let me figure out the corresponding null space again. So I'm going to subtract 4 plus 2i from the main diagonal of my matrix up here, capital A, right? So I'm subtracting 4 plus 2i. So 9 minus the quantity 4 plus 2i would be 5 minus 2i. And then I have a 29. And then I have a minus 1. And then I have minus 1 minus the quantity 4 plus 2i. That's minus 5 minus 2i. So this is your matrix, right? Now, remember, this matrix is definitely not invertible. The determinant was 0. So this is not an invertible matrix. So you know that even though it doesn't look like it anymore, these two rows have to be multiples of each other. So I'm going to cross one of them off, okay? Let me, it doesn't matter which one we cross off. Yeah, I guess it doesn't matter. I'm just going to go ahead and cross off the first one, okay? And now what I'm going to do is I'm going to write down my eigenvector right here that's going to go with the second row. And what my eigenvector is going to be is 5 plus 2i and negative 1. You know, I think I want to stop for a minute and point something out that I don't know that I've really ever quite explained to you guys, but you're going to thank me for this, I hope. Maybe you'll be upset I didn't show this to you sooner. Let's imagine, first of all, just for a 2 by 2 matrix, you've got, you know, some row here and you crossed off the second row or whatever. And this is all that you're left with. And you're trying to do a null space for something that looks like this. You see, what you can do for that is you can actually build your eigenvector in the following way. Just switch the two numbers a and b. So put the b first and put the a second and change the sign of one of them. Okay, so this is a trick that always works when you have two unknowns, or in this case, two variables that you are playing with each other. So here we have a and b. So you're really trying to solve ax plus by equals 0. That's really what this row of this matrix equates to as an equation. A is some constant, b is some constant, and you're solving for x and y. Well, I think everybody would agree if I put negative b in for x and a in for y, the left side cancels to 0. Isn't that great? So this vector where x is equal to negative b and y is equal to a works. And that's all that we're looking for here, guys, is some vector that will work, right? And so that's actually, you can imagine that's basically what I did right here. Here's my, my a and my b. So the negative of b is just, change the negatives to positive. 5 plus 2i, and then recopy what a is on the bottom. It works just great. So that's a clever trick, because especially when your matrix has complex numbers in it, it's gonna be tedious to actually like set up free variables and try to solve by back substitution. And this little sort of recipe in the lower right corner of my board is just saves you some headaches of doing any calculations. You just take these two numbers a and b, you swap them and change the sign of one of them. It's just a trick. The first 10 times that I taught Math 250B, I didn't use it. I didn't really appreciate it enough. Even as a professor, I didn't appreciate how much it saves time for students to just be able to write down the vector immediately. So that's what we're doing right here. Okay, so we've got an eigenpair, and then of course we have another eigenpair. So we also have, we have lambda equals 4 minus 2i, but you probably remember that the eigenvector that goes with the conjugate eigenvalue is just the conjugate. It's just the conjugate of the eigenvector that you found for the original eigenvalue. So I can just take this vector 5 plus 2i and -1 and change it to 5 minus 2i and -1. There you go. All right, so now let me come back. We have found our eigenpairs for this. Here's the system we're solving up here in the top right corner. Let me get some of this older calculation. Like I said, these take a lot of writing, and I just don't have as much room as I would like. So what we would get now is the following. So what we would have is, x of t equals, well, actually, let me be a little more careful with this. Let me just call this x of t equals e to the 4 plus 2i times t times the vector 5 plus 2i -1. Let me just write that down. So this is just, e to the lambda t times v. Right? That's all I've done here. E to the lambda t times v. And I'm just focusing on this one. Incidentally, guys, turns out we don't actually even really need to keep track of the other one. It's not going to end up being important because we're going to be able to generate two linearly independent solutions just from what I have up here so far. So normally, guys, one eigenpair produces one solution. But what I want you to think of right now is we have two eigenpairs. Here's one eigenpair right here. Here's another eigenpair right here. These two eigenpairs are going to produce two solutions collectively. And I'm going to get both of them if I just study what I have right here. Now, here's the deal. This is not an acceptable answer because it has I in it. I wouldn't know how to graph it. I wouldn't know what it really means, raising e to some imaginary power. As an engineer who is focused on real solutions, right, that we can touch and feel and draw graphs of and take derivatives of and all sorts of other math, this is not going to be satisfactory. Okay, so this is not the end of this problem. We have to take this e to the lambda t times v and do a little bit more work with it. Let me show you what that work is. Okay, the first thing is I'm going to extract the e to the 4t completely out into the front, and then I have e to the, well, it would be 2t times I. And then I'm going to just recopy the second vector, like that. Okay, and now what I'm going to do next is I'm going to use I'm going to use that Euler formula for e to the I theta. Remember this one? We talked about this actually in chapter 8 briefly. I know I didn't go into a lot of detail about this, but e to the I theta has a very nice mathematical representation. This can be proven using power series, for example, which I'm not going to go into in this class. But this is the so-called Euler's formula right here. So I'm going to use that formula to try to help myself out up here. Okay, so here I have e to the I theta. My theta in this case is 2t. So let's plug that in to the Euler formula right here in my calculation, okay? By the way, this is the hard part mostly for today's talk. So feel free to slow me down or ask me to repeat something, or if you need a question, just jump in. I totally appreciate that. I'm going to use that Euler formula right here. Cosine of 2t plus I times the sine of 2t. So notice I've got a real piece and an imaginary piece right here. I am going to do the same thing with the vector part. I'm going to break this up into a real piece. This is going to be the vector that does not have I in it, and then plus an imaginary piece. I'm going to basically, it's sort of like busting out the I. I'm going to bust this I out, and it's going to leave me with a 2 and a 0. Okay, so this part over here on the right is really just this vector again. But what I did is I took out the parts that don't have I and separated them from the parts that do have I. Now, we're still not happy with this answer because we still have I in it. But what we're going to do next, guys, is we are going to multiply this out. Okay? I am going to multiply this thing out. That would normally be called FOIL, right? You want to sort of FOIL this thing out, except I'm going to call it something else. I'm going to call it Floyd. I'm going to, right now, I am going to Floyd this out. And you're going to see why I'm going to do it like this in a second. The first and the last are going to go together. Let's use some big braces and let's see how this works out. The first part is cosine of 2t times 5 negative 1. Okay? That's just the first of the first, right? So this term times this term. Now, I'm going to jump to the last next. The last one is I sine 2t. So I'm going to do this one right here. I sine 2t times I 2, 0. Now, the beautiful thing is that I squared, you see the I times the I squared is negative 1. So this becomes a minus sine of 2t times the vector 2, 0. Okay? So this is the first and this is the last. The reason you want to put those together is that there is no I anywhere in that part of the answer. So that's the F and the L of the Floyd. Now let's do the outers and inners. Both the outers and the inners are going to have an I in them, and I'm going to factor it out right away. So the outer term is cosine of 2t times 2, 0. Hope you guys can read that okay. I'll hold this in just a little bit here. Okay, and then plus the inner term is sine of 2t. That's sine of 2t times 5 negative 1. All right. So there you have it. This is the outer term, and this is the inner term. Okay? So I Floyd it out. I didn't FOIL it, I Floyd it. And I did it in that way because I want to combine the two terms that don't have I in them, and then I combine the two terms that do have I in them. Okay? Now, we are still not quite done. We are still not happy with this answer because there is still an I right there. Okay? So I'm going to just finish this up, by the way, guys, and then we will take a short break. I know I've been talking for a little while. This is just a little bit of a complicated situation. When you have complex eigenpairs, e to the lambda t times v, right, has I in it. That's the problem. So we're going to go through this whole procedure right now, and I'm going to squeeze the I out of it. It turns out that if we go back to the very beginning and we replace this function with e to the 4 minus 2i t, and we use the conjugate eigenvector 5 minus 2i and -1, and we do this same whole thing again, we'll get another expression that's very similar to this one. And it'll also have an I in it. We don't have to actually do any of that. Simply what we've done so far is good enough. But what I'm telling you, and hopefully you'll believe me, is that if we were to go back and repeat the whole Floyd process with the conjugate eigenvalue eigenvector pair, we could get another answer kind of like this written down. And it turns out that by doing linear combinations of those two answers, we can actually get rid of the I completely, which is what we want to do. One of the solutions is going to be this one right here. So x1 of t. Okay, you don't have to derive this. I'm just telling you that this is what's going to happen. x1 of t is just going to be the FL part, right? It's going to be e to the 4t times cosine of 2t times 5 -1 minus the sine of 2t times 2, 0. That's your first solution that you're looking for. Okay, and then the second solution, I guess I'm going to have to write it up here at the top. This is going to be x2 of t. Is just going to be, you're going to keep the e to the 4t in it. You've got to have that because that's factored out of everything here. It's just going to be the O and the I part, but without the I. Without the I. So it's just going to be cosine of 2t times 2, 0 plus sine of 2t times 5 -1. There's your second sort of basic solution there. Okay, so sorry, I wrote the first one way at the bottom here and the second one at the top up here. Okay, so my final answer now. So notice that we only had to work with 4 plus 2i and its eigenvector. We never had to deal with the other one. We never had to deal with the conjugate. We just take this whole Floyd business and extract two real solutions directly from this. And we're good to go. So here's the answer now. X of t equals C1 times, here's the first solution, e to the 4t times, you know what, I'm going to take this opportunity, especially since I have a small board, to point out that this part in parentheses could actually be compressed. You don't have to do this, but if you read across the top of this vector here, what you see is that you have 5 cosine of 2t minus 2 sine of 2t. So just going right across the top, 5 times the cosine of 2t minus 2 times the sine of 2t. I'm just writing that right here. Okay, I'll bring this in a little closer here maybe. And then for the second line, I'm just going to read across the bottom of this vector. And I see that I just have minus the cosine of 2t. This sort of compressed expression, you'll find this in the back of the book sometimes just to save space. You don't have to do the compression if you don't want to. You can just write it down the way I did here at the bottom, and that would be just fine. Okay, so that's the first term. Now let me raise my screen back up. I'm going to take the second vector, x2 of t, and add that here. So c2 e to the 4t. And I may as well compress this one also, okay? So on top I have 2 cosine of 2t plus 5 sine of 2t. And on the bottom I have negative the sine of 2t. Okay, so there is your final answer, finally, with no I in it anywhere. Make sure that you never have an I in your final answer to any of these problems, because you can get rid of that I by sort of Floyding it out. This whole Floyd procedure is how you get that done. Okay, this looks fabulous. Does anybody have any questions so far? Okay, one thing that maybe gets lost when you get so tangled up in these calculations, and I admit that when you have complex eigenvalue, eigenvector pairs, this does get a bit messy, but it's mostly just a procedure. You just have to understand how to do the Floyd and work through this step-by-step process, and you'll get the right answer here. But one of the things that gets lost when you're doing all of this heavy calculation is sort of, what does this answer mean again? What am I supposed to take away? So this is the solution to this system. What is this telling me? Like, how does the math like reflect reality or reflect some physical problem? So what I would like to do, guys, is take a break for a few minutes right now, probably about maybe almost 10-minute break. I think we can do that. And then after the break, I'm going to come back and talk about the geometric insight. I'm going to draw some pictures, and I'm going to want you guys to know this stuff. So this isn't just going to be sort of a side thing. This is going to be something I will ask you about in the exams coming up, is sort of, what does this physically mean? What is the geometry of the solutions? And what am I supposed to sort of take away the big picture of the solution to a system like this? So let's take a 10-minute break. At 1:20, I'm going to start talking about the geometric / application side of all of the math that we've just learned. Okay? So go ahead and take a 10-minute break, and then I'll be back with you at 1:20. Okay, sorry guys, I got caught up out in my kitchen for a second. Hope that you guys are all there and ready to pick back up again. Did anybody have any questions on either of those examples or any of that material sort of in the first half of today's talk at all? It'll take a little practice to get comfortable with the Floyd idea, but it's pretty mechanical. It's conceptually not that bad. You just have to be careful, take it step by step, show all of your work, and do that Floyd business very, very carefully as well. So you'll have some homework problems to practice that on, and I think that'll be good. Again, for today's homework, I'm not going to take questions during class today, but I am going to go to my office hours after class. And you guys, if you have some things you'd like to talk about with the homework, you can certainly reach me over there. What I'd rather do with the sort of the half hour I have left today is I want to talk a little bit. I'm still in section 9.4, but I want to talk a little bit about the geometry or some of the physical insight, I guess, that we can get from these linear systems that we're studying. So I want to start with an easy one, which is one that we did a little bit earlier today. We had a linear system, and the coefficient matrix A is right here. I just recopied it for you. So this is already in your notes. We found the eigenpairs, which I've listed here and here, right? 5 and -3. We found the eigenvectors that go with those eigenvalues. And then we very immediately wrote down the general solution. So this one was nice. There were no complex numbers. We didn't have to do the Floyd thing. We could literally just find the eigenpairs and go straight to the answer. Okay, but what does this answer mean? Like, how am I supposed to think about this answer? So what I'm going to do is I'm going to try and draw a picture to show you a little bit about what this really means. So let me come up here and I'm going to draw an XY axis. Okay, so we're going to draw a picture now to sort of reflect what the situation is. And I want to look at this general solution, and I'm going to sketch some of these solutions. Now remember, this is an infinite set of solutions, right? Because you have infinitely many choices for C1 and C2. But every time I pick, let's just say we pick some specific solutions here. I'm going to pick 4 of them in particular. So the first one is C1 equals 1 and C2 equals 0. I want to make a real easy special case here. If I plug in C1 equals 1 and C2 equals 0, I'm going to get x of t equals e to the 5t times the vector 1, 1. Okay, so I'm just putting a 1 right here, and I'm zeroing out the second term. Now take a look at this solution. It's got 2 components. By the way, this e to the 5t could be multiplied through this vector if we wanted to. But let me actually just draw that vector onto my xy plane. There's the vector 1, 1 right there. Okay, it's just that point 1, 1. Now at t equals 0, if I plug in time to be 0, I do actually get the point 1, 1, which is exactly this point that I just drew right there. But what happens as time evolves? As time goes forward? As time goes forward from 0, e to the 5t grows. And that is a scalar, a growing scalar that multiplies this vector 1, 1. So what that does is it makes that vector 1, 1 longer, right? So as time goes on, that vector gets longer. And I'm going to draw arrows to show that the vectors are going longer, outward, right? So this is sort of showing motion to this problem now. The t, the time variable, is part of what we're studying here. By the way, if we went negative with time, if time went backwards towards negative, we would see, if we sort of did this video in reverse, that the particle, or whatever, the solution I should say, would get very close to the origin. So it would look like that. So this picture that I've drawn on my XY plane is showing one of the solution curves to this linear system. It's one solution. Let's draw another one. Let's do, for a second solution, let's do C1 equals -1 and C2 equals 0. If I do that, I'm going to get negative e to the 5t times 1, 1 again. So it's literally the same thing except with a minus sign in front of what we had before. A minus sign applied to a vector just turns it around, right? So this is the solution number 1 right here. Let me just label that with a 1. What's going to happen for solution 2 is that I'm just going to flip solution 1 completely 180 degrees around. Now the solution starts out somewhere down here in the lower left quadrant, and as time goes on, it just goes farther and farther away from the origin along that straight line. Okay. Let's take another case. What if C1 is equal to 0 and C2 is equal to 1? Okay, so I'm looking at this box. If I put 0 for C1 and a 1 for C2, I'm going to get x of t equals e to the negative 3t times 7, 1. Okay. So now what's that going to look like? Well, let me plot the point 7, 1, 2, 3, 4, 5, 6, 7, and 1. Somewhere right about there. I'm sorry, my axes aren't really drawn to scale here. This is the point 7, 1. And at time 0, that's what x of 0 would be. It would be 7, 1. As time goes forward now, look at this negative in front of the 3t. As time gets bigger, e to the negative bigger number actually shrinks the vector, right? Because e to a negative number would be like less than 1. It shrinks the vector, and what happens therefore is that you get this vector, but the vector is getting smaller, so I'm drawing my arrows coming towards the origin, right? This is solution curve number 3 right here. Okay, so the third one shows those arrows. That's supposed to be a straight line, by the way. It's coming straight towards the origin. And finally, if C1 is equal to 0 and C2 is equal to -1, right? I don't quite have all the room I'd like down here. But in this case, x of t would be the negative of e to the negative 3t times 7, 1. So I'm just writing the negative of what I had on the third line. Okay. And all that that's going to do is it's just going to take curve number 3 up here at the top right of the board and flip it across the x-axis. So we're going to go 1, 2, 3, 4, 5, 6, 7, and -1 somewhere down here. And now again, all of the solution curves, this is number 4, they all go towards the origin and along that straight line that goes through the point -7, -1. So I have drawn 4 specific solutions. As you know, there are infinitely many different solutions, aren't there? And, you know, what if x of 0 put me somewhere like right here, or over here, or here, right? There's so many different scenarios of where I could start from. I know that if I start on this line, I'll stay on that line. Or if I start on this line, I'll stay on that line. But if I'm somewhere else, what I have to do is sort of imagine solution curves that are consistent with the ones I've already drawn. So for example, this one right here, It's not going to be straight, but the arrows are going to kind of go in that direction, right? Something like this. Same thing down here. The arrows will be going more from right to left, right? This is not something that we expect perfection on when we draw these things, but this is what you'd have. Also, right in here, you'd have a curve that sort of does a pretty sharp U-turn because it's a little bit tighter space in these little regions. Okay? What I have just drawn on the board here, guys, is something called a phase portrait. It is a phase portrait. And let me tell you what I think is the best way for you to think about a phase portrait. Imagine that this is the water flow on the surface of a lake. And the arrows are telling you the currents in that water, how it's moving, right? How the water is moving through the lake. This is the surface of the lake. And let's say you come along with a feather and you drop a feather onto the top of the lake, right? And you want to watch how the feather floats through the lake, right? So you drop this feather maybe right here, for example, right? How does it flow? Well, you simply follow the lines of the phase portrait, and that's going to tell you the path of that feather. So this feather would probably go something like this, right? So this is showing you what the feather is going to do. If the feather started at the origin, if you happen to put it right at the very middle here, it just sits there. Okay, there's no current at all right at 0, 0. Okay, but this is the idea of a phase portrait. You're watching the flow of the surface of a lake. Every time you drop a feather onto the surface somewhere, that's like giving an initial condition. It's saying, where is your feather going to start its path at time 0? Okay, so maybe this is where that was, right here. At t equals 0, my feather starts out here. And all we want to know is, okay, as time goes forward, what is the path of that feather? Each one of these blue curves, and I don't know if you can tell the difference between the blue curves and the black curves, but these blue curves are like particular solutions that I'm specifically drawing onto my phase portrait based on some initial position, initial condition, right? So that's kind of the idea behind this. This type of phase portrait here, where some of the lines are coming towards the origin and others are going away from the origin, this is called a saddle. So this is I'm sorry, I should be more precise. I'm sorry. Sorry. What I want to say is the origin is a saddle point. It's like a saddle point because, you know, from certain directions, the arrows are coming in towards the origin, but then in other directions, the arrows are going away from the origin. Right, so this is the whole idea here. Does that make sense? Actually, why is it a saddle, though? Like, why are some of the arrows coming in and some of them are going out? What really dictates that? Like, what really determines whether the arrows are coming in or whether they're going out? Can somebody take a look at anything we've done here? Do you see what is it that really determines whether I'm drawing my arrows towards the origin or away from the origin? Just want to make sure somebody's alive out there. Any thoughts on that? Yeah, Caesar, you're on the right. You have the right idea. The positive. You see here we have an eigenvalue with a +5, And here we had an eigenvalue with a -3. And you see down here, we ended up with an e to the 5t and an e to the -3t. The positives and negatives are what we're determining whether the arrows were going out or coming in. It all has to do with the signs of those eigenvalues. Okay, so in the case where both of the lambdas are positive, where one of the lambdas is positive and one of the lambdas is negative, you get this saddle point every single time. Incidentally, I'm only going to be doing this geometric insight for 2x2 systems. Only for 2x2 systems. So once things are in 3D or higher, it's very hard to draw pictures and to really make physical sense of it. And I think we can get the idea with just these 2x2 systems. So let me make a quick note there, because I think we came up with a pretty good idea. So notes, in fact, I'll make a couple of notes here. Okay, so the first one is if lambda 1 is greater than 0 and lambda 2 is less than 0, then the origin, 0, 0, is a saddle point. Then we get what's called a saddle point. So if one of the lambdas is positive and one of them's negative, we'll get a saddle. But let's think about some other things that could happen. What if lambda 1 and lambda 2 are both greater than 0? Then 0, 0 is I'm going to fill that in just a second. But before I fill it in, I'm going to draw a picture of what that phase portrait might look like. Okay, so I'm going to erase this one over here. Kind of got the idea there behind that one. So in this case, see, if I was going to draw the phase portrait in case 2, here's my xy plane, right? Whatever those eigenvector directions were, because the lambdas are both greater than 0, all of the arrows are going to point away from the origin. And so it turns out that you just get a totally dispersive effect of the phase portrait having all of the arrows coming out. In this case, when both lambdas are positive, this is roughly what you're going to get. And in this case, 0, 0 is what is called a source point. In this case, the origin is a source. Okay, so we have a saddle, we have a source, and then I have a third one for you. If lambda 1 and lambda 2 are both less than 0, then 0, 0 is of course, the picture, let me get a picture of this. In this case, all of the arrows, as I'm sure you could expect, they're all coming towards the origin now because we have a negative, we have e to a negative times t, which approaches 0. So in this situation, this is case 3, right? So here's case 2, here's case 3. In this type of phase portrait, everything is getting sucked towards the origin. If you drop your feather in to your phase portrait anywhere on the lake, it'll get sucked to the origin no matter where it started from, right? This is called a sink. It's a sink. So 0, 0 is a sink point. Just like watching water go down a drain, right? Everything gets sucked into that drain. It gets sucked into that sink, and so it makes sense to call it a sink point. So we have saddle points, source points, and sink points. We're not done yet. This is not the only possible scenarios, but these are 3 of them. that can come up. Okay, is everybody with me so far? Okay, because the other scenario, I only have about 10 minutes left, but I have plenty of time to sort of finish this off. The other scenario, guys, is what if the eigenvalues are complex numbers? Right? Because that could also happen. So I'm going to continue my notes over here, and we're going to talk about that for a minute. Okay? Remember, for a 2 by 2 system, you only have 2 lambdas. So they're either both positive, they're both negative, there's one of each, or they are imaginary. So that is what I want to look at here. So I'll call this case 4. Suppose lambda equals A plus or minus BI. I want to think about the phase portrait in this case. So here, I want to assume that B is not 0. We want to actually have a legitimate complex number here in this situation. Okay, well, let's look at what the solution, you know, what the formula for the solution is here again. Let's go back to the actual math of it. Remember that it was, you know, e to the lambda t times v. This was the eigenvalue eigenvector pair being placed into the solution. If you don't know anything else from what we've tried to learn today, this is what you should definitely know, right? E to the lambda t times v. Extremely important. And if I feed that in to my expression here, this is e to the, you know, a plus or minus bi t times v. And I'm going to pull out the e to the at part of it. And then I'm going to do my Euler formula, cosine of bt plus or minus I times the sine of bt, right? And then over here, the eigenvector, remember that we also split that up into a real and imaginary part, which I'm going to call R and S here. This is just the same thing we were doing in that example before the break with complex eigenvalues. We come up with this whole thing, and then remember that for this last part here, we're going to Floyd it out, right? We use the Floyd on this part. But the thing is, I'm not going to go any further with actually Floyding it out, because what I want you to notice about it is that this vector over here is a constant. It doesn't change, right? And this part here oscillates every, whatever it is, 2 pi units of time. Sines and cosines, as you know, they repeat every 2 pi units. So, you know, cosine of bt and sine of bt, those are going to kind of go around in a circle, more or less. It's not going to change. So this whole part right here, that I've just underlined is periodic. The behavior repeats itself after 2 pi units of inputs of sine and cosine go by. Right? It's periodic, but it's getting magnified by e to the at. This is a scalar out in front that has this effect of stretching or shrinking whatever the rest of this vector is. So what is this going to look like geometrically? What is it going to actually be? It turns out, I'm going to do sort of 3 cases. So this is for A, B, and C. If A is greater than 0, when you look at this expression, if A is positive, then this e to the at scalar is going to be getting bigger. If A is positive, e to the at grows bigger. And so whatever is going on with this sort of circular periodic thing, I don't know exactly what it is, maybe it's something like that, right? Without the stretch factor, this is maybe what it would be, some weird shape like that. But it's getting stretched by e to the at. So instead of just tracing a figure that repeats itself, it's actually got to be getting stretched in all sides as time goes on, right? So if, let's just say for the sake of discussion that this thing was tracing out a circle. The periodic part was just literally a circle. But then you start stretching that circle every moment of time, the circle gets bigger and bigger radius. That is called a spiral, right? That is called a spiral. And if A is greater than 0, it is actually an outward oriented spiral. In other words, I'm going to draw some arrows on my spiral here. The points on my solution curve are getting farther and farther away from the origin. So this is called an so 0, 0 is an unstable spiral. So if you have complex numbers for your eigenvalues and the real part is positive, you have an unstable spiral when you draw the phase portrait. And again, there's not just one spiral, right? If I drop my feather right here onto my phase portrait and I let my feather float through time, it's just going to float in a spiral. It's going to spiral around on the surface of the lake, right? So you're dropping feathers into these phase portraits and you're asking what is the behavior of those, of the solution, of the path of that feather. Okay, real quick, we're almost out of time. Let me just wrap up a couple more things and then I'm going to say a quick word about what I expect you to be able to do. If A is less than 0, in that case, 0, 0 is a stable spiral. So that would be a stable spiral. And then finally, if A is equal to 0, so a stable spiral just means that of course, the arrows are pointing inward. If you drop the feather into a stable spiral, it's going to spiral inward towards the origin as time goes on, as opposed to spiraling outward towards infinity. Finally, if A is equal to 0, then 0, 0 is a circle point. These should say, I'm sorry, these should say like point on the end of them usually. Unstable spiral point, stable spiral point, and circle point. Now, it doesn't mean that it's literally a circle, but it definitely just periodically repeats over itself. It's not getting any bigger. It's not getting any smaller, because if A is 0, take a look. If A is 0, you don't have this e to the at here, and you just get a periodic behavior. The feather just goes in a circle forever. It just retraces on top of itself forever. Okay? Couple last notes, and then I'm going to let you go. The first thing is, if I ask you if 0, 0 is a saddle, a source, a sink, a stable spiral, an unstable spiral, or a circle, that's 6 possibilities. If I ask you that question, all you have to do to answer it is find the eigenvalues. You don't have to go through a whole lot of deep, heavy math calculation. The eigenvalues alone are all that are needed to decide whether you have a source, a sink, a saddle, a spiral in, a spiral out, or a circle, right? That's all you need are the eigenvalues. That's the first comment. The second comment is, I do want you to be able to draw the phase portraits. You know, on an exam, it's a little tough to say, draw the phase portrait for the system, because it's like, well, how many curves are you supposed to draw, right? But I am going to hold you responsible for this sort of qualitative section, this geometric section. And if I don't ask you to draw a phase portrait, I might ask you to do a matching exercise where I give you some phase portraits and I give you some matrices and I say, match up the matrices with the phase portraits. I could do something like that. Or I might just ask you to draw one particular solution that a feather is tracing out when it's dropped into the phase portrait. So without drawing the whole phase portrait, to be able to sort of draw a particular solution on that phase portrait. Kind of like when we were originally just drawing the individual curves at the very beginning there when I first started doing that. That sort of thing is pretty standard and I think should be pretty relatively straightforward. Anyway, do people have any questions on this? I wanted to give you a little geometry behind what's like really going on here, so we're not just blown away by the math alone. Okay, that's all I've got for today. I want to remind you, please start Saturday's homework before Thursday so that you can ask me questions on Thursday about it. We're going to have a whole nother pretty heavy section to go through on Thursday, section 9.5. And if you've had a chance to get 9.4 at least started or cleared out of your plate a little bit, it'll make things go a lot easier towards the end of the week. So that's just my advice for you to help keep on track. In a couple minutes after I finish erasing here, I'm going to go over to my Zoom office hours. I'd love to talk to you over there. Thank you all for coming today and for your patience and attention. I hope that it's making sense, but if not, please do keep in touch. Come to my office hours and we'll talk about it. I can talk one-on-one and we can get things sorted out, okay? So thank you very much for today, guys, and I'll see you again Thursday at the latest. Bye for now.